Some probably be home. I'm thinking of something completely.
Yeah, I can't pronounce it. Yeah, I thought you did all of this. Is that what Mr. Smith? Yeah, he said he hates.
My apologies. Mine is
Ours just got
I
filed.
mean,
my conclusion is so vague.
from what Addie's saying, it doesn't even sound like she's giving us, like, she's not said let's have.
Half of the information we need.
And even if it is on there, nobody's gonna remember what her life color is or what.
No, I just want to. That's what I said. That's what brown.
I never care what the time
Like,
is.
that's okay, good. I know. Doctor dates or times or like.
I like her weight is like,
Yeah,
he'll work with me, cause I'm.
you didn't even start, so you
I
just
said,
like, like, can't even.
He is, he's a good
I don't
teacher.
know.
What?
Like,
Not
he'll
really.
work with me,
Everybody's
not
done
doing my work.
I did it yesterday.
Like, I'm, like, when I take the test.
When you said Thursday, I was like, I really, it's so pretty outside. I do not want to sit in here another hour doing by myself. I'll do tomorrow. And what did I do Friday? My parents dragged me to town all day. I didn't get home until 10:30. And I still had assignments that would do at midnight. So I did those. Those are priority, right? And then I was like, okay, it's time to do it tomorrow. Saturday,
You know, you got like a
I'm
test a
like,
week, do
I'll
that
do
tomorrow.
this, then I'll do like half of it.
Then like, I'll
Or
give you
half
next
of it,
week.
but the first page was your name stuff that I counted as one of my pages.
Okay, I like.
I was like, oh, I guess I got one page.
Like, I'm probably going to call my like,
Yeah.
five.
Yeah, and I think.
And then,
Like, I didn't do my thing, I think. Like, hey,
I don't know.
If it's you, because you're.
I don't do my.
Did you have any idea, like, at the end of the lesson, on Friday, what was going on?
No. Oh my gosh, no.
I understood where you want 4.1, but. We weren't supposed to turn out the North End today, were we?
Not 4.2.
4.1. Okay.
Being serious?
I have been down 5 times and my grade is going to conclude that.
What did you get?
Like a 60.
Dude, I got like a, so after the 4-point term, I got like a 72 or something like that.
That's about what I'm saying.
Yeah.
If he counts it 5 times, both of our grades are going to
If
conclude.
he counts it 5 times, he might. No! I'm gonna have to take all 4 sides. We're gonna have to find out what career drugs.
It gets better. Each week, it's a little bit better each week. Just that they have. And then he goes back to being no grandma. He said,
That's where you get mad.
no, not for me, because I said it's not a problem for me. You have to have a heart for that, and Mr. Common doesn't have one. But it is hard for Mr. Common. Which is also why he continues to chew the absolute living daylights out of her. Because he knows that if he does that with me, he'll get jacked up. Not even really jacked up, he just doesn't like being pushed somehow. Leaving my crap everywhere. It's close.
I think I did, sounds good.
Yeah, I imagine it would take you about that. So, that's just gonna be our success. With that. Has that goes, right? Okay, Mr. Cotton's gonna try really hard not to fill that board today for each problem that I have to do. But I make no promises. I'll go ahead and I'll just mention it now. We're still struggling with attendance from this section when it comes to the live streams. So I'll make it perfectly perfectly clear. I don't care if you go back and rewatch them on your own time. There's not a reason for you showing up in the morning, you're getting marked absent. The whole reason why I'm keeping the marked as done button is to make sure that you are watching it at some point. If you're not watching it live, then you are at least watching it at some point. But that marked as done button is not really doing much for your attendance anymore. You need to be in live stream sessions. There's only 1 or 2 people that have talked to me about other issues. And if you have one of those issues, then you can talk with me and we'll work something else out. But you need to be in the sessions. Some of you are really good about it, by the way, like not talking to all of you. Some of you, you're spectacular. You haven't missed a single one, which is great. Some of us, we've only shown up to like 1 or 2, and that ain't going to continue to work as things are going to progressively get more difficult. So we're going to go ahead. We're going to begin here today with slide 13. Oh, before we do, we shouldn't have any homework questions because if we came on Friday, we had our opportunity to ask homework questions on 4.1, but I'll go ahead and open it up anyway. Does anybody have anything from 4.1 they'd like to discuss? Good. Let's go ahead. We're going to begin then with slide 13, which is where we left off on Friday because we didn't finish all of 4.2, unfortunately, but that's okay. It just means that things will work out a little nicer, a little cleaner this week for our quiz and test. Mr. Cotton might have just a little bit anticipated that this might have to be a 2-day kind of deal, though we will absolutely finish today. We will absolutely finish today. So I want to return to this problem. How do we do this problem? How are we going to evaluate this summation here? How did I do it before? I did this problem at the end of the live stream, did it at the end of class on Friday. How do we do it? Anne-Marie?
You took 1 over n squared out and left it with 10i and then plus 10
So we did something like this, right?
Yeah.
Where we took the 1 over n squared out. We have our I equal to 1 as we go towards an n value of 10, right? So this was our first step. What do we do after this?
Then you use the formula that's given, which is 1 over n squared parentheses n times parentheses n plus 1 all over 2 plus 1n.
Before I did that, I did split them, right?
Yeah.
And then we did the formula. So what was this first one again? This is going to be
n times n plus 1.
all over.
2
And this one here is, of course,
plus 1 times n.
1 times n. The constant times however many n values we need to add together, right? And then, of course, we're just going to simply plug in what the n value, of course, was. The n value here is 10, right? So we're looking at 1 over 100, 10 times 11 over 2, plus 10. We ended up with 100, and I believe this ended up being 65. Yep. And that gave us 0.65 as our answer. Questions here? Okay. So that takes us back through slide 13. Of course, on slide 13, I didn't actually plug the n value back in. Now, right here is where my work on the slide differs from what we did in class. On the slide, I sent n squared through and reduced each fraction and then plugged in my 10. Here, I just went ahead and plugged in 10 and reduced. We'll talk about why I would do it that way and why I would do it this way for different situations here today. But in the meantime, do this one. Move on to slide 14 and do this one. Do it without me. See how far you can get along with it. Let's get to work. Let's get going. Who feels like they know how to start this problem? Alan, what are we going to do to begin?
Do you take out the 4 over N4?
I would. That's what I would have remembered. I would distribute out or factor out. 4 over n to the 4th power. 201. And that leaves us I squared times I minus 1. What did you do with the rest of that,
I
Alan?
distributed the I squared.
Yeah, I think that makes a lot of sense because I haven't told you how to do these with multiplication yet. Nor do I think I'm really going to, because that's ultimately not what we're going to want to do with them. So I would recommend sending that through. Of course, when we send that through, that's going to become I to the 3rd minus I squared, right? So we'll rewrite this as something like this, where we have our summation of the I to the 3rd minus the summation of I squared. Is everyone okay with what we've done? Okay, I need some formulas. Who's got some formulas for me? Somebody other than Adam. Who's got some formulas for me? Caleb, what you got? What's the I cubed formula?
It's n squared times n plus 1 quantity squared all over 4.
So we got n squared and then n plus 1 quantity squared, right? All over 4. What's our squared formula?
N times n plus 1 times 2n plus 1 all over 6.
Are we all okay so far? Okay. What do you want to do? I don't think putting in 200 is the right call at this stage. I don't think putting in 200 at this stage is the right call. We're just going to end up with massive numbers, massive decimals, and things like that. We can't simplify this down before we do that, which is what I recommend that you do. What I would actually do is I would distribute this in. I would send this 4n back in. When I send it into the first term, the 4's cancel. Some n's are going to cancel, and I'm going to be left with n squared on the bottom and n plus 1 quantity squared on the top. When I take it to the second one, the 4 is not going to cancel, but it is going to reduce to 2/3. And this will give me an n cubed on the bottom and cancel out that n on the top, making n plus 1 and 2n plus 1. That's probably where I would begin at the very least. Simplify it down some. At any point, we can plug this in. Let's make no mistake. At any point, you can plug it in. You can't get the right answer. You can do 200 in at the very step here in red. You can do it now. You can keep going if you want. We can make this into common denominators and continue to reduce. What do we get? Anybody have an answer for me? Miss Grice, what you got?
Is it 1.3?
Let's find out. I'm going to plug everything in. I got 1.003 as well. 1.003 as well. This is probably the point where I would stop personally. I don't see those going together very evenly, very nicely. I got n squared and n cubed now, which means that I'll have to bring it back up to n to the 6th power to get a common denominator, which isn't really going to help me, so I would probably leave it where it's at and plug it and evaluate here. Rather than evaluating up here in red, where it's still complicated. In fact, it's overly complicated at that point. This is probably, I think, the easiest step here when it comes to substituting it. Questions? Okay. So, let's talk about mixing the two together. So, as we had a limit definition for derivatives, we have a limit definition for integrals. It is the limit of a summation. It is the limit of a summation. So, this is what we're going to do. Instead of having n equal a specific number, we'll set n equal to infinite and reduce down like we did in the previous chapter where we talked about section 3.5 where we set limits at infinity. Now most of this is going to operate relatively the same way. Relatively the same way as we set up our problem here. We have the limit as n approaches infinity of the summation of n and I equal to 1. And then we have our terms here. We have 2i over n and 2 over n, like so. Are we all okay with where we're going to begin? Just copying down the problem, really. Okay, what do you think we should do first? What's common sense dictate to do first, gang? Parker?
Multiply them together.
Yep, let's multiply them together. Let's simplify what we have inside here. So, Parker, when we multiply this together, what are we going to be looking at here?
4i over n squared.
Okay, what do you think we're going to do next?
Factor out the 4 over n squared.
Factor out the 4 over n squared. I like it. Gives me the limit as n approaches infinity of 4 over n squared. We still have our summation in here. Bye-bye. Are we all okay with Parker's work so far? Okay. I think you're on track, sir. What do you think we're going to do next?
Is there a formula?
I think there's a formula for I. What's the formula for I? Go back through your notes if you need to. Go back through your notes if you need to. Brian, can you help him out?
Isn't it n parentheses n plus 1 over n? 102.
N plus 1 over 2. We have our 4 n squared as the limit of n approaches infinity. Are we all okay with our work thus far? Okay, what do you think we're about to do now? I think we should send it back together and then continue to reduce. Okay, so let's bring this back in. When we multiply this in, we're going to be left with the limit as n approaches infinity. We're going to have 2n plus 1 over, of course, n. Let's actually distribute that 2 through, so that way it becomes 2n plus 2. Are we all okay with our work thus far? Comfortable, yes or no? Okay. Last thing. Can we evaluate this limit? If we evaluate this limit, what do we get? 2. Because we have even degree, top to bottom, yes? So we'll look at the coefficients of those leading terms. This is 2 over 1, which of course gives us the limit here of 2. Questions here? Concerns here? Okay, now I'm going to use this example as our lead into what we're going to do. So where we started this lesson, for those of you that tuned in or went back and watched it on Friday, was we started by talking about finding the area underneath a curve using rectangles, yes? And we talked about how wide those rectangles need to be versus how tall they need to be. And we talked about left hand, right hand, low, high, and middle, right? We talked about all those different ways we could set up the x values and why that gives us different y values and how those are either underestimations or overestimations and things like that, right? We recall doing this. Okay. So what we are going to do is we are going to blend the two together because we said this, doing it by hand as we started out, worked for a small number of rectangles, but it wasn't going to work for a big number of rectangles. By evidence of the 2 summation formulas I did, we most certainly wouldn't want to have to do 10 x values, plug them all in, solve them all down by hand, just to do the area formula, right? Likewise, the last one I just did was 200. You most certainly don't want to do 200. And now we're talking about doing infinitely many. So what we're going to talk about here is as we say we're going to use an infinite number of rectangles. Now, obviously, we can't actually use infinitely many rectangles, right? But as we approach infinite number of rectangles, what will the overall area approach? Because the more we use, the more accurate it will be, right? Those little differences from the graph to the actual area are going to get smaller and smaller and smaller, right? We saw that already by the work we did on Friday. So what this problem is going to show is very simply, this is the summation of an area formula. We're going to take area 1 plus area 2 plus area 3 all the way through area 1,124, all the way through area 9 million, all the way through infinite number of areas of rectangles. Does that make sense? Where I have 2 things there, length times width, if you will, to represent my formula. Does that make sense? So the things that we're going to have to set here are the same relative parameters. We're going to need to find, on average, what the width of each of these rectangles should look like. We're going to find what the height of each of these rectangles are going to look like. And we will do a very similar summation limit mixture to do this. This is what an integral is. It is the limit of a summation type question. Whereas where we had derivatives, which was the limit of a slope, now we have limits of summations. Okay? So let's go ahead. Let's do one more like this before we jump into doing them back with the graphs and things like that. Let's do one more like this, just to make sure we're comfortable, make sure we're confident before we get back to doing f of x and x and things like that. I want to make sure we're feeling good with these summation questions. I have one too many limits in there. I don't know why that's copied over twice there, but that should only just be one limit, by the way. It's a little bit of a typo there. It shouldn't be 2 limits, just one there.
For this one, would you just distribute the square?
I'll try to FOIL it out. What I'm doing. Oh, I know why there's two limits there. It's because one of them is supposed to be my summation. That's my fault there. This is where the summation is supposed to be I equal to 1 to n. That's what happened. Who wants to help us out here? Caleb, help us out. What are we gonna do?
I foiled the I ones.
Foil that out. I also imagine that you move this 1 over n cubed down. Okay, so we FOIL this up. We're gonna get I squared minus 2I plus 1. Okay, now what?
That's what I got.
Okay, so what I'm going to tell you is the next thing we should do is treat each one of these individually. Okay, so we've got the limit. This is a problem that, like I said earlier, I'm going to try really hard not to fill this whole board with. 1 over n cubed. We have parentheses. Our first summation. Nothing special about that one. We can do a nice formula for that one in a second. Minus the summation of n, I equal 1, 2i. So what I'm going to do here, Michaela, is I'm just going to take this 2, and I'm just going to bring it outside of that summation. Okay? That way it's just I. And then plus the summation of n, I equal 1 of course, 1. Everybody okay so far? So if we're following along with my slides here, we've done the first step here where we copied down the problem, the second step. And now we're going to start the third step, which is going to be our substitution. Yes, sir?
Why do you bring 2 outside the summation?
Because I feel like it. I could have left it in and it would just stay on the top of the numerator. But I like to bring it out because that way it helps me reduce down. That's what you see there in green, which is what I'm about to do. Okay? Okay, we need some formulas for each of these. Let's start with the first one. What's the first one?
N times n plus 1 times 2n plus 1 over 6.
Minus, we have our 2, and then we have n times n plus 1, yes? And all this, of course, is over 2, right? So as Luke said, why did I take that out? Because I felt like I could have left it in, it'll just be 2n. Either way, it's going to cancel with the 2 on the bottom. I'm going to do that right now before I do too much else. And then, of course, this is just going to be 1 times n, right, or n. Are we all okay here? Yes, no, maybe so? Michaela, what do you think we're going to do next? I don't think so, not yet. Not yet. How about we send the 1 over n cubed back through? I think that's what we're going to want to do next. Let's send that back through. So what ends up happening, of course, this n cancels, and I have n plus 1 over 2n plus 1 over 6n squared. This is going to become minus n plus 1 over n squared, and plus 1 over n squared. Are we all okay here? Sir?
We do the n squared.
For which one?
For the, like,
Middle or last?
the middle one.
Middle. N cubed brings me down to 1 over n squared. Other questions? Other concerns? Okay. Now let's do the limit. These two are going to be easy. We have a higher degree on the bottom. As we talked about 3.5, what does that mean for those two? Where are they going to go? Go, John.
It'll be 0.
They're going to be 0. Of course, this one, when I FOIL out that top, I'm going to get n squared, am I not? When I actually FOIL that, so I will actually have an equal degree on top and bottom. So we do need at least that first term from our FOILing to see what the lead coefficients are going to be. What's the first term going to come out here to be? 2n squared, right? Okay, so we're looking at the lead coefficients here, which would be 2 over 6, or 1/3. Yes? Okay? 1/3 minus 0 plus 0 equals 1/3. Hey, look at that. I only used half the boards this time. Of course, I showed less work this time around than I did last year. Questions? Okay. It's this scale of a problem that we're going to be doing, if not higher scale than this. Which is why I need you to be comfortable with these summation limit mixtures, because this is what we're going to do to finish out today. And anybody other than the one person that I know of try all of the 4.2 homework yet? Okay, so I know one person did. Ryan, how did those last couple problems go?
They were pretty tough.
They were pretty tough. They take up a lot of space, don't they? Yep, because they're these, but kind of like on steroids. So, just to refresh what I talked about on the previous problem. Let's move on to the next slide. As my work finishes it out. Moving on to the next slide, slide 17. Help us wrap this up. This is the limit definition for an area. Limit definition for an integral. So first we need our function to be continuous. We need our function to be continuous that we're talking about. And we're going to need it to be non-negative over this stretch. We need it to be over the x-axis. Now we could do it under the x-axis, but I haven't told you how to do that yet. Not very hard, just throw a negative out in front. But nonetheless, let's focus on the easy ones today. If we have this, then we have some area that is going to be bounded between a high endpoint and a low endpoint, making a nice section of the graph that we will then do the area of. The area here will be the limit of the summation, as I told you on the previous problem. What we are going to do is we're going to set this up as two separate things. We're going to have f of c sub I, f of c sub I. This is going to be the given height at any point, at any particular rectangle or another rectangle. That's what the f of C sub I represents when we look at our area. Delta X is going to be the overall change in X, or the overall width that we are going to be talking about each individual rectangle. Are we okay? These are two things that we are going to have to do before we are able to do a problem like this. So we're going to be adding at least 1 or 2 steps before we do this. We must set what the width is going to be. We are going to set what the height function is going to be. You guys are going to be so much happier when we look at the faster way to do this tomorrow when we talk about Riemann sums. But for now, you need to know how to do this using the limit definition. Just as we talked about it before, we need to talk about it with integrals as well. Questions here before we move along and start the first problems? All right, Mr. Kaufman's going to get loose here for this. I'm just kidding. Okay, we're going to use the limit process. Moving on to our next slide. What is it? Slide 18. We're going to use the limit process to express the area for x squared plus 1 on the interval 0 to 3 for this value. Now, for those of you that are doing real good here, you might recall that we did this problem on Friday, and we did it with a set number of rectangles. So we'll talk about the difference now between the two answers. So, first, let's go ahead. Let's get our function going here. We got y equal to x squared plus 1. We're looking 0 to 3. So, if you want, you can, of course, draw a little graph here to help us keep in mind what we're doing. We're looking at this function right here between 0 and 3 as our set. Okay? Are we all okay with a rough graph to get us started? I think that even though we're still using infinite many rectangles, it can still be beneficial to help us here. Okay, let's set the delta x, the overall width of these. Delta x, okay, that's going to be b minus a over n. Okay, so that's 3 minus 0 over n, which is, of course, 3 over n. Are we all okay with this? This should be pretty straightforward. We're just taking the endpoints, subtracting them on the top, and then we're going to divide that by n, because n represents how many rectangles we're going to use, which is infinite right now, right? So, next thing we need to do is set what our ci is going to be. This is going to be our y values, or their interpretation thereof. What we're going to take is take the endpoints and our I together. So we're going to have ci is 0, our a, plus 3 over n times I, which is just ci is 3I over n. Are we okay with this? This is the given x that we're going to plug in at any particular point to get us a y value. Does that make sense? That's what ci represents, is what would we be plugging in at any particular one point in time or another to generate the y value. This is the part, this c sub I is the part that we are changing when we talk about left hand, right hand, lower, upper, middle. This is the part that we were talking about before, and now we're just saying, okay, over this infinite amount of rectangles, which one specifically do I need to plug in to get a specific rectangle's height back? So if I want the height of rectangle 20, I'll put in 3 times 20 over n. Does that make sense to everyone? What CI represents? Okay. Okay, we need to actually find what the function will be with this C sub I. So f of x is x squared plus 1. We're going to bring this in. So this becomes f of C sub I is going to be 3i n squared plus 1. This is what our height function is going to look like. So we have width in blue, we have height now in red. To the limit, we will go. To the limit, we will go. So, limit, as n approaches infinite, the summation of I equal to 1 is infinite of 3n times 3i squared n plus 1 is what we're looking at. I have it written in a couple more steps there, but I'm going to try to save and conserve my workspace here. I recommend going ahead and simplifying this a little bit before we get too far ahead of ourselves. Summation, I equals 1, infinite. I'm going to keep the 3n out. On the board, I have it on the back half on this, or excuse me, on the TV, I have it behind. Right now, I have it in front. It doesn't make a difference. I'm going to go ahead and send this through. This is going to become 9i squared over n squared plus 1. Is everybody okay so far? And at this point, now we're back to what we did on the past couple probes. So how should we finish this out? I've done a lot of the preliminary work. What do you think we should do to finish this summation? Not to say that there's no wrong answers. There are wrong answers, but there's no bad guesses. Caleb, you got something for us? What do you think?
Should you distribute?
We could try. You want to try it? We'll go for it. Let's distribute that through. If I distribute that through, what's it going to look like? Well, it's going to look like 27i squared over n to the third plus 3 over n. Are we happy with that or satisfied with that?
No need to isolate the I squared.
We're eventually going to want to isolate that I squared, right? So that way we can use the formula for it, right? So is it better to do that now, or is it better to go back a step? What do you think? You guys are smart kids. Tell me what you think. I shouldn't even say kids. You guys are adults now. You've grown.
I think probably go back and stuff.
Then go back a step. I would take that 3 over n out. I would not send it through, Caleb. I would keep that separate. Okay? It doesn't do a whole lot of good sending it in. Because we don't need it to be inside the summation in the first place. What we want is we want to isolate the I squared in the summation, which means everything else we want to pull out so that way it's between the limit and sum. Okay? So that's the next step that I've done is I'm taking this unnecessary multiplier and I brought it out. And now I have 9i squared n squared plus 1. Okay, now what do we want to do with this 9i squared n squared? I tried to show you a little bit on the last one when Luke asked me why did I send that 2 out, so I'm trying to show you what I'm going to do here. What do we think? What do we got? What do we think?
Just take out the 9 over n squared.
We could separate those two sums, right? And then take the 9n squared out of the first one. So let's see that in action here. This is the limit as n approaches infinity, the 3 over n. We're going to have our first sum, 9n squared, I squared, right? It's our first term. And then we'll have the second limit as we approach infinity, I equals 1 of 1. Make that the number 1 because it kind of looks like an I. Okay. Well, they're isolated. Can I swap the formula now? Okay. What formula are we going to use?
N plus 1, 2n plus 1 makes 3.
A little bit slower, Alex, for them, please.
N times n plus 1 times 2n plus 1 over 6.
That's our I squared formula, right? And then for this one, it's just a constant, which is n times the constant, or 1 times n, which will just be a straight out n. So, and then we have this in parentheses, 9n squared, then all of this in parentheses, and 3n. Are we having fun yet? Mr. Kaufman is. I'm almost out of space, though. I guess I should have did more on this side. Oh, well. Next problem. Okay? Whose head hurts right now? Parker? It's all good. It's going to start getting easier right about now. Because now we're going to start sending things through and simplifying it back down. So, first, let's go ahead and let's send the 3n in. We can send the 3n in, or we send the 9n squared in first. Which one would you like to do? End of the day, multiplying isn't going to make much of a difference which one goes through first. On this board, I sent 3n in first because I think that makes more sense to me, but of course, to each their own. I'm going to go ahead and redo that here. I'm going to send the 3n in first because I'll multiply out here. Give me 27 n cubed n plus 1, 2n plus 1 all over 6. And then when I take this to the second term, I'm just going to get 3. I take that to my second term, I'm just going to get 3. The ends will cancel, and I'll be left with just a straight 3. Are we all comfortable so far? Okay, let's continue reducing our first term here. I can distribute this in, and I'm going to get n squared, because this one will cancel with that one. I'll take a 3 from both. That's going to give me 2, and that's going to be 9. And I have n plus 1, 2n plus 1. Oh, n plus 3. Are we all okay so far with my simplification? Let's see where Mr. Kaufman left off on his slides here. That's our work there in red is where I'm at currently with my simplifying. At this point, I'm going to go ahead and evaluate the limit. I'm going to plug in my infinite. And of course, I'll see that I have same degree top and bottom for my first term, right? Same degree top and bottom. So of course, we're going to need to figure out what this first term actually would come out to be. When we FOIL this together, this would give me 2n squared times my 9 would give me 18. So when I plug in that infinite, I'm looking at 18 over 2 plus 3 is the evaluated version of my limit. 18 over 2 is, of course, 9. My final answer is 12. Did you think that we were going to get a solid, nicely number out of this? We did, though. We did, though. Oh, man, the faces some of you guys are making is just faces of pain and anguish. And I am sorry. I have tried to make it as easy as I can. It's not an easy thing to do, though. Questions here, in person or on live stream? Do we need to go back through any of it, or are we okay? I can't help us if we don't ask questions. So I'm assuming that our silence is agreement, that we're fine. Okay then. Onward to the next problem. To the next problem. We have 4 minus x squared. So, looking at this problem, 4 minus x squared, what we have here is we have a parabola that's been raised up 4, and a parabola that will have zeros at 2 and negative 2, which is actually the area, that looks terrible, but that's okay, which is actually the area that we're after here, right? So there's 2 ways we could do this. We could do the whole thing left to right, from negative 2 to 2. Or we could just cut it in half and double it and use that idea instead. Is everyone okay with these 2 ideas? Because we are directly on the x-axis, we can use the symmetrical properties here to help us. So that's what I intend to do here. Make this a little bit easier for myself. Make this just a little bit easier for myself since it is right smack on the axis and I can do a nice symmetrical set here. That's what I will do. So I'm going to modify this a little bit from the set negative 2 to 2. I'm going to make it run 2 through 0. I'm only going to look at this half right here, and then I'll double it at the end. Does that make sense? So that allows us to set up our delta x, which I can't remember what color I used for that anymore. I'm going to say it was blue. I'm going to set up my delta x, which is b minus a all over n. So b is my new starting point, which I've said is going to be 0. And my starting point is going to be, 2 minus 0 over n, if I write things correctly. So I have 2n as my average width. Are we okay with this so far? Okay? This makes finding ci just a little bit easier for me. This is going to make defining ci just a little bit easier for me. It's going to be 0, or a, plus my 2 over n times I, which is just going to be 2i over n. If I can make this c sub I part easier, that's what I want to do, because ultimately that's going to make evaluating the limit easier when the time comes to do the summation and all that stuff, because this is what has to get back into this formula. So this is what we want to kind of be more simplified as this c sub I. Of course, this gives me ci is 2i over n. I don't know why I wrote that. I already have it up there. So we're going to go ahead. We are going to plug this into my equation. I like to do that separately. So this is 4 minus 2i over n quantity squared. Let's start our limit. of the sum, I equal 1, goes to infinite. We'll have f of ci times our delta x 2 over n. Are we all comfortable with what I've done? Now there is something that we need to do out in front of this. This is only half of this, right? So we need to double this limit, so times 2. 2 times. Because this is only technically this half, right? We want both halves of this, right?
To show that you need to redistribute, you just put the number in front of the limit.
Yeah, I'm just going to put it out in front of the limit. Because whatever this is only going to represent half of it. So I'll just double my answer at the end. Okay? And honestly, that's probably when I'll deal with the 2 is at the very, very, very end. I'm not even going to bother setting it in or trying to put it into summation unless I absolutely desperately need it. Okay? Turn our attention to this monstrosity. First thing I'm going to do is I'm also going to bring that 2n out in between the limit and summation because it doesn't need to be in the summation in the first place because the whole deal here is to isolate I. And there's no i's in it, so it needs to leave the sum. And then we're going to have our 4 minus our 2i squared over n. Finally squared. Okay, so far, let's reduce, let's simplify. 2 times the limit of 2 over n. Of course, this n goes to infinity. Our summation of 4 minus the summation infinite I equal 1. We'll reduce this, and we're going to bring out a 4n squared as our multiplier and be left with I squared inside. Are we okay with that? For anybody that's not seeing that, I can do it right here. This would reduce down to be 4i squared over n squared. So this is where I'm getting that 4 over n squared out in front of my summation. Is everyone okay with that? That's a little bit out of place. I know I'm blocking sight for some of you. Okay, what's the I squared formula again?
N times n plus 1 times 2n plus 1 over 6.
So I have 4 times n, or 4n, because that's a constant, minus 4n squared times n minus our 4n squared, and then our n plus 1, 2n plus 1, all over 6. Correct? Correct? The formula gave me n times n plus 1 over 2n plus all that junk, right? Okay. Now what? Good, John.
Put in the 2n.
Yeah, let's start working on simplifying this mess, right? Okay, you want to send the 2n through first? That's fine. Do that. I'm just going to take it to the coefficient there, to that multiplier, rather than trying to send it into the whole monstrous fraction here. So that gives me 2 times the limit. N goes to infinity. This is going to become 8, right? Minus, that's going to become 8n cubed. And then n plus 1, 2n plus 1, all over 6. A little bit more simplifying to go here, as I'm running out of space. I guess I'm going to have to carry it over here. Also, my purple marker is dying. I'm going to go see if I got a different one. I bet I do. That's one. Let's send this other multiplier in. So we got 2 times the limit as n approaches infinity of 8 minus, when I send that through, it's going to become 4/3. What's going to happen with my numbers there? And I'm going to have n squared, and then n plus 1, 2n plus 1. If it helps you to know, this is always going to spit out 2n squared plus 3n plus 1 when you multiply those two together. So it's going to spit out 2n squared plus 3n plus 1. Okay? We can go ahead and evaluate the limit now, can't we? Right? What's the limit spit out? What's the limit going to spit out? 8 and
8/3.
okay. Finish it.
With the 8 minus 8/3 gives you negative 16/3, and then times 2 you get negative 32/3. Right?
Positive.
Oh,
If I'm going to put this over 3, this is 24/3
yeah,
minus
yeah.
8/3, which is
The positive 32/3. Yeah.
there it is. We made it there eventually. Yeah, there will be no shortchanging my work on these problems. Because even if you want to skip steps, which by the way, I am skipping steps in here. It's not like I'm showing every single little thing that's happening. When I distribute, I'm not showing how everything cancels exactly down. I'm not showing every single little detail. This is legitimately the minimum level of work I would expect from you guys on one of these problems. This is legitimately the minimum level of work I would expect for one of these types of problems. Questions here? What time we got? Good. Are we ready to move on? Another slide, another problem. Slide 20. If we want to go forward, maybe.
That's the last slide, isn't it?
Oh, that's not what I wanted to be the last slide. What happened to the one I added today?
The dates and meter.
Well, crap.
You write it on the board.
I guess I'll just let you off the hook. I'll just let you off the hook. This has been enough, I think. This has been enough. Why don't you go ahead and get started with your 4.2 homework. And we'll let our kids on live stream, we'll let them peace out unless they have questions. Go ahead and use this time to get started with your homework. I highly recommend starting at the end and working your way forward. For those of you that haven't started yet. And my live stream students, I will see you all on Thursday.